my name is Nako Nakatsuka. I'm a fourth year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck. Now we move on to the final chapter of this review, which is the thermodynamics and kinetics of organic reactions. And so this material builds extensively on the thermodynamic and kinetics foundations that we previously went over in the past chapters. And the concept covered here apply to all organic reactions. But as an introduction to organic reactions, we will focus mainly on reactions that involve carbon-carbon double bonds, which are called alkenes. And they look like so. But let's start off today by talking about nucleophiles and electrophiles. So all throughout this chemistry series, we've talked about where electrons are and how they flow, right? And this is the basis of chemistry, where opposite charges attract and like charges repel. And basically, electrons flow from an electron-rich area to an electron-poor area. And today we'll officially name the types of species that are considered electron-rich and electron-poor. And they're called nucleophiles and electrophiles. So let's start out by talking about nucleophiles. This comes from nucleus loving, since the term philes stands for liking something, loving something. And so I like to remember nucleophiles as nucleus loving, which is a positive charge, right? And so a nucleophile is a reactant that provides a pair of electrons to form a new covalent bond. And so they are electron donors. So does this sound familiar? Because we talked about Lewis bases, right? And nucleus-loving nucleophiles are actually Lewis bases, since they donate electrons. So when we talk about electrophilicity, which comes from loving electrons, now we talk about electrophiles. So an electrophile is a species that accepts a pair of electrons to form new bonds. And so it likes negative charge, and they are electron acceptors. So again, this sounds familiar, and it's because we talked about Lewis acids before. So nucleophiles are often shown as Nu, that stands for nucleophiles, and with 2 electrons that it can donate. Also, it's often shown as minus. On the other hand, electrophiles are often written as E for electrophile or E+, the positive charge wanting to attract the negative charge. So if you look at this nucleophilic substitution going on right here, don't worry about what chemical each of these groups are, but you can see the general way in which this reaction happens. So here we have an R group attached to an X, where there's an electronegativity difference, so this is slightly negatively charged and slightly positively charged. And so the nucleophile is going to attack the positively charged guy, since it's nucleus loving and it likes the positive charge. And so when it attacks this guy, this arrow indicates that this guy is leaving. This bond is being broken and a new bond is being formed. And so in this case, the R group is considered the electrophile, because now a new bond is being formed with the R group, and so it's being an electron acceptor that the nucleophile is donating. And you can see the same exact reaction happening right here, but in this case, the only difference is that the nucleophile doesn't have the negative charge right here, and so in turn, this group is going to end up being positively charged because this didn't start out with a negative charge. And so by bonding this neutral atom to this R group, now it's going to be positively charged. And so as you can see, this is a very simple way to show where things are being donated and where electrons are being accepted. At this point, I also wanted to show you guys the difference between certain arrows. And so to give more detail in an organic reaction mechanism, we show what kind of electrons are being moved by using arrows. And so if you have 2 electrons moving from here to here, I'm going to draw an arrow with a full end. But if I have one electron that's moving from here to here, then it's going to be half an arrowhead. And so showing where the electrons are going from here to here, for example, and then from here to here, this full head shows that 2 electrons are being moved. This half arrowhead shows that only 1 is being moved. So this is a very useful thing to use to show the different mechanisms. I wanted to further show how we push arrows. To give an example, we have CH3, CH, double bonded to CH, CH3. And if we add this to HBr, that looks like so. And then it forms CH3, CH, with a positive charge on this carbon, CH, CH3, plus a bromine ion that's negatively charged. So now if someone asked you to draw the arrows for what's happening, there's a correct way and an incorrect way to do this. So the correct way is to show that this double bond is being broken, right? Since there's a single bond here now. And so this bond is being broken and it's getting given to this hydrogen, which in turn breaks this bond and gives those electrons to the bromine, so that the bromine ends up with 2 extra electrons and ends up with a negative charge. On the other hand, some people might draw something like this, where the arrow goes from the carbon to the hydrogen and then to the bromine. And this is wrong because the electrons are coming from the double bond that's being broken. So always make sure you make the arrows go from the origin of the electron source to where the electrons are going. And so the arrows are supposed to represent the electron flow and the proposed mechanism. And this electron flow is based on electrostatics. And what that means is that the arrows point away from electron-rich regions and towards electron-deficient regions. So arrows point away from electron-rich regions, and arrows point towards electron-deficient regions. So again, let's do an example. If we had CH3, CH3, and we have a double bond here, an oxygen and a hydrogen, and this is initially positively charged, and this goes to CH3, CO, 2 electron pairs now, and plus H+. So clearly you can see that this hydrogen was removed, and now it has another pair of electrons. So the correct way to draw the arrows would be, it's breaking this bond and going to the oxygen, right? That's correct. It would be incorrect to write it like this, where the hydrogen, the electrons are just going somewhere, because the arrow always has to go from the electron-rich to the electron-deficient. To show how much thermodynamics plays a role in organic chemistry, I wanted to show you guys this complex reaction coordinate diagram, which is a mouthful, but it's actually something very familiar to you guys because I went over it in kinetics. So remember, we start out with reactants, and then the reactants have to overcome some kind of energy barrier, which we call the activation energy, to reach a transition state, and then it makes the products. And so right here, you can see these 2 molecules where hydrogen is represented by this white circle and oxygen is represented by this red circle. And we also have CH3Br, so CH3, and a bromine is this bigger red group. So we have CH3Br, and there's a minus sign right here. And then the transition state is HO, bound to the methyl group, CH3, but also the bromine is also attached. And then finally for the products, we have OH bound to CH3, and then Br minus by itself. But what this is showing is that due to the arrows being pushed, where electrons are being accepted and donated, as you can see right here, you create this transition state where both the OH group and the bromine are simultaneously attached before one is completely formed and one is completely broken, so that you end up with the bromine being the leaving group and this being the new product. So this is a really simple way to show how with the change in the Gibbs free energy, as it's increasing up the y-axis, you can go from the reactants to the products and show how the different states look by pushing the arrows and drawing the coordination complex or the transition state as having both bonds still attached.